Okay, so this is project test number 1, video number 3, and will be problems 21 to 30. And 90% of the people who have a particular disease will have a positive result on a given diagnostic test. 90% of the people who do not have the disease will have a negative result on this test. If 5% of a certain population has the disease, what percent of the population would test positive for the disease. So anytime I see a problem where I have a lot of information, I try to organize it. And in this particular case, I know I have positive diseases and positive tests and negative tests, and I have disease and not disease. So this gives me the suggestion that I'm probably going to need to make some sort of table for this. All right. And since I know that I have two different things going on, I'm going to make my little window table because I believe this is where I'm going with this. Whenever I set up one of these, I need to read this thing real carefully and determine if there's a value that's only tied to one of my variables. Well, what are my variables? Well, I have disease, whether someone has a disease or not, and then whether or not they test positive or not. So I have test results, and I have whether they're diseased. So let's read this again. 90% of the people who have a particular disease will test positive. So this 90% is tied to disease and positive. So this is a two variable, and I'm not looking for two variables at this point. Looking for a number tied to a singular variable. Then it says 90% of the people who do not have the disease will have a negative result. Once again, this is tied to two variables, not what I'm looking for. 5% of a certain population has the disease. That is tied to a singular variable. I know it's tied to a singular variable because it doesn't mention test results. All it does is say, hey, 5% have the disease. So this is going to be disease. This is not disease. And I'm going to go ahead and say this makes this 0.05. And 1 minus that is 0.95. And we know that that makes up 100% of the population. So once I have those values, I can write them small. I'm going to write 0.05 here and 0.05 there. I'm just going to bring them up like this. This is going to be 0.95. And this will also be 0.95. So 90% of the population who have a disease will test positive. So my test results are going to be positive and negative. At that point, we have disease our variables disease, and we have test results. So 90% of the people who have a particular disease will have a positive result. So disease and positive is right here. So this is going to be 0.90. And this will be 1 minus 0.90. Now I'm going to go ahead and multiply those values out because we can check them as we multiply them. So we're going to go 0.05 times 0.9, and I end up getting 0.045. And when I multiply this, I end up going 0.05 times 0.1, and I get 0.005. Now here's what I meant by checking them. I should be able to add these two values. So let's check it out. And they add up to 0.05. So this plus this, they sum together. That looks like that's a pretty good chance that we did not make a mistake there. Then it says 90% of the people who do not have the disease, so not disease, will test negative. So this 90% is going here because no disease and testing negative is here. 1 minus that is right there. So 0.9 times 0.95 is 0.855. And then if I take the 0.95 times this 0.1, I again get 0.095. Well, I should be able to check these two out by adding them up. And they add up to 0.95, so I feel pretty good that this is correct. So now we're going to go ahead and sum our rows. And we're going to go 0.045 plus 0.095. Oops. 0.045 plus 0.095, and that equals 0.14. And adding these up, it's going to be 0.005 plus 0.855 equals 0.86. And these two sum together to go one whole. I think I'm pretty positive that I got my table together correctly. Then it says, what percent of the population would test positive for the disease? They have no condition on this. They just want to know the percent that test positive for the disease. Well, the percent that test positive is 14%. So for number 21, our answer is D. All right, the real important type of problem shows up almost every year. It takes a little time to set up, but really not that difficult if you'll follow the steps. The key is isolating the variable, the number that's associated with one variable. And in this case, the number associated with one variable is 5%. All right, number 22. A recent survey concluded that the proportion of American teenagers who have a cell phone is 0.27. All right. So we have a survey that this is their conclusion. The true population proportion of American teenagers who have a cell phone is 0.29. So they're telling us this is a true population. This is not from the survey. So this is a p hat. They get 0.27, but from a true population, it's really 0.29. For samples of size, and by the way, this is a key word. For samples, they didn't say this sample, they meant for all samples because they used the plural. So for all samples of size 1,000 are selected at random from the population, what would be the mean? So if I averaged all of the samples, including this one, what would the average be? Well, the average would be 0.29. All right, so the average would be 0.29. So in this case, we're looking at, and then they ask for, what do they ask for? What are the mean and standard deviation? So they're telling us this is going to be the center. So that tells us right now we're getting rid of the 27. So if we do the average of all of them, we're going to get 29%. And remember, this right here is my standard error when we're talking about multiple samples. All right, so this is letter D, because basically p hat minus p naught over p naught q naught or n. All right, so basically whenever we know this, if we know this, we have to use that because we assume it to be true. And remember, if you do it over and over again, it will be that case. All right, and then this is a case where we have multiple samples, so we know we're not referring to the p hat. Number 23, a marketing company wants to estimate the proportion of consumers in a certain region of the country who would react favorably to a new marketing campaign. Further, the company wants to estimate to have a margin of error of no more than 5% with 90% confidence of the following, which is the closest to the minimum number of consumers needed to obtain the estimate with desired precision. All right, so we have a marketing company with, and we're looking for a proportion here. All right, so basically, let me reread that real quickly. Percent with 90%. Pause this for just a second. Okay, I was looking for this word and I could not see it. The word I was looking for was proportion. All right, so basically my confidence interval formula is p hat plus or minus z star p hat q hat n. Now remember, when we're working with a confidence interval, these are always going to be p hat and q hat because we don't know what the population proportion is. We're making an estimate. Well, this right here is my margin of error. And they're telling me that they want a margin of error of no more than 5%. So we need to start plugging in what we know. We know our margin of error is going to be 0.05. And we know that they want to do a 90% confidence interval, which means I need to get my Z star. And I can do that quickly from the calculator, second bars, inverse norm. My area is going to be parenthesis 1 minus the 0.90, because that's our confidence level, divided by 2. And since this is Z, it's always going to have a mean of 0, standard deviation of 1 when we're working with the Z. So we end up with 1.645. Your life will be better if you make it positive. So 1.645. We know we're looking for N, so I can go ahead and write that down. But what I don't see is they did not give me a p-hat. I have no estimate. When I have no estimate, I'm going to use 0.5 because that gives me my largest standard deviation, which is my worst case. So I'm going to divide both sides of the equation by 1.645. And I know this is not the best math, but I'm going to go ahead and say that I'm going to square that just because it makes life easier if I do it right now. So this becomes 0.25 over N equals 0.05, 1.645. This is squared. So 0.05 divided by 1.645, and I'm going to go ahead and square that. And 0.25 divided by this value will give me N. So 0.25 divided by, and I end up getting N equals 270.60. Now, this is an easy one because you know you're going to round up with a 0.60. But if it had been a 0.10, you still round up. So you always round up. In this case, our answer is going to be letter B for 271. 24. Traffic data revealed that 35% of automobiles traveling along a portion of an interstate highway were exceeding the speed limit. Using a highway camera and license plate information, it was also determined that 52% of sports cars were also speeding along the same proportion of the highway. What's the probability that a randomly selected car along the same proportion was a speeding sports car? So here we have two different things. We have cars that are speeding and we have sports cars. So they want to know the proportion of the two here. So what is the probability a randomly selected car was speeding on the highway? Well, so I'm like, you know what? Let's go to the table. We have two things. So I'm going to make this little table up, and I need to figure out which one goes with one variable. Traffic data revealed that 35% of the automobiles on a highway were speeding. Oh, okay. So on the highway, we have cars speeding, not speeding, because that's associated with one variable, and this is 35%. So 35% were speeding. That means 65% were not speeding. This is going to be one whole. Well, that was easy because that's associated with one variable, which was just cars. Then we have, it was also determined that 52% of sports cars were also speeding. So we're going to have sports cars speeding, sports cars not speeding. And this is associated with one variable. But there's no relationship between them. And because I don't know the proportion of cars on a highway that are sports cars, I can't do this problem. I would need to know the proportion of cars on the highway that are sports cars in order to do this problem. Tricky problem. They wanted to set you up, but since you don't know the proportion of sports cars on the highway, you couldn't do it. If they had given you that, you could use the table and solve it. 25. In a large school district, 16 of 85 randomly selected students or seniors play varsity sports. In the same district, 19 of 67 randomly selected high school juniors play a varsity sport. A 95% confidence interval for the difference between the proportion of high school seniors who play varsity sport and juniors in the districts is calculated. What is the standard error of the difference? So first off, let's figure out what our confidence interval formula looks like. So we're going to have p hat seniors minus p hat juniors plus or minus z star p hat seniors q hat seniors over the sample size of seniors plus p hat juniors q hat juniors over the sample size of juniors. All right, so they're asking for the standard error. The margin of error includes z star, but that's not what we want. We want the standard error, which is only this portion right here. All right, this is a little bit of an ugly problem to do. So we're going to go ahead and do this, but it's going to be a little bit trashy. So first off, our proportion of seniors is 16 out of 85. Well, if I take 85 and I subtract 16, I end up getting 69. So my Q hat seniors is going to be 69 over 85. And my number of seniors was just 85. So this is this first fraction here. Plus I need to do the second fraction, which is with the juniors. You know, the juniors is 19 out of 67. And 67 minus 19 is 48. So this is 48 over 67. And my number of juniors is 67. And then we're going to throw all of this under the radical. So like I said, this is not a very pretty little exercise, but we can go ahead and get it done because of the calculator. So 16 divided by 85 times 69 divided by 85. Now I'm going to take that value and divide it by 85. So that gives me this value of this fraction, 0.00179. I'm going to write it down, although it's stored in my calculator. So this is 0.00177 plus, then I need to do the other part, which is the juniors, which is going to be 19 over 67 times 48 divided by 67. And then that whole thing divided by 67. And I get 0.00303. I'm going to add these two values together and take the square root. So plus, and then add it to this one. And I'll take the square root. And I end up getting 0.0694. And my closest value is letter B at 0.0695. Kind of an ugly question, but very doable. Just have to stick with it. All right, problem number 26. The number of points scored in a game has a probability distribution below. So basically, the probability of scoring 0 points is 40%. The probability of 1 point is 30%. The probability of 2 points is 30%. And if we add these up, 0.4 plus 0.3 plus 0.3 equals one whole valid probability distribution. So the number of points obtained in one game is independent of those of the next game. All right, so it doesn't matter how many times we do it. They're telling us that each game is independent. When the game is played twice, the sum of the number of points could be 0, 1, 2, 3, or 4. Anytime they tell me we're doing something twice, or I have two variables, I'm probably going to need to make a table of some sort of sample space. If y represents the sampling distribution of the sum of the scores when the game is played twice, for which value of y will probability be greater? Well, I'm playing it twice, so what are my combinations? Well, I could get a 0, 0. 0 on the first game, 0 on the second game, 0 on the first game and 1 point on the second game, or 0 on the first game and 2 points. That's all the possibilities with 0. Or I could get a 1 on the first game and a 0 on the second game, a 1 on the first and 1 on the second, 1 on the first and 2 on the second, or I can get 2 on the first, none on the second, 2 on the first, 1 on the second, or I can get 2, 2. So those are my combinations. And 0 plus 0 sums to 0. So what's the likelihood that I get 0 points? Well, the likelihood that I get 0 points means I have to get a 0 and a 0. So what's the probability of getting a 0 of 0.4? On the first game, it's 0.4. But I also have to get 0 on the second game. And since they're independent, I can go ahead and multiply them. And this is 0.16. So there's a 16% chance that that would happen. The probability of getting 1 point means 0 and 1 and 1 and 0. So this would be 1 point. What's the probability of getting 0? Well, 0.4. But then I need a 1 on the second game, and that's 0.3. But there's 2 ways I can get it. I could get a 1 on the first, so this is 0.3 times 0.4. 0.4 times 0.3 is 0.12. Add these up, and they sum up to 0.24. So there's a 24% chance that I only get 1 point. Well, what's the probability that I get 2 points? Well, 2 points are these 3 methods, which is a 0 and a 2, which means 0.4 times a 0.3. A 1 and a 1, well, probability of 1 is 0.3. And then another 1 is 0.3. And then probability of a 2 and a 0. So plus 0.3 times 0.4. That's 0.33 when I add all of that up. So we know it's not 0. We know it's not 1 because 2 is the biggest so far. So 2 has the largest probability. Continuing on, we go to number 3. Well, with number 3, I can get that by getting a 1 and a 2 or a 2 and a 1. The probability of a 1 is 0.3. The probability of a 2 is 0.3. And then swapping that around and doing it the other way is 0.3 times 0.3. And that's 0.18. Well, that's less than this, so it can't be 3. And then we have the probability of getting a 4. Well, the only way to get a 4 is to get 2 2s. Well, that's 0.3 times 0.3, which is 0.12. So that's smaller. So the largest value at 0.33 is 2. Now, checking this out, if I add these up, it should add up to 1 whole. So 0.16 plus 0.24 plus 0.33 plus 0.18 plus 0.12. So obviously I have somewhere, oh, excuse me, that's not 0.12, this is 0.09. Try that again. 0.16 plus 0.24 plus 0.33 plus 0.18 plus 0.09. So that adds up to 1 whole, and the fact that it adds up to 1 whole probably means I set this up and solved it correctly. And this was the greatest probability, and so we were looking for the one with the greatest probability, and that equals 2. But they had wanted the one with the least probability, that's 0.09, which would have been a sum of 4. Okay, so our answer to number 26 is C. About to skip a problem. Number 27. Each person in a random sample of adults indicated his or her favorite color. The results shown in the table below are reported by age group of respondents. if choice of color is independent, so if they're independent, that tells us we can multiply which of the following expression is equal to the expected number of respondents who are aged 30 to 50, who inclusive, who prefer green. So we're saying, hey, what would we expect if they were independent? Well, if they're independent, we can multiply them. So, and we are looking for who are 30 to 50 and prefer green. So we're looking at the green category, and we're aged 30 to 50. So they're independent. They're asking us for the expected value. So they're asking us to multiply probabilities. Well, the two probabilities are the 30 to 50. So the probability of 30 to 50 intersect the probability of preferred probability of green. Well, the probability of 30 to 50 is 108 over 314. And the probability of green is 99 over 314. And when we multiply those, we're not going to see any of our answers because they didn't ask us for the probability. They asked us for the expected value. Well, expected value, so let's go ahead and do this. If we were to multiply this, remember our formula for expected value is just this. Expected value is n times p. Well, that's my probability, so I need to multiply it by my sample size. Well, what was my sample size? 314. So I need to come back and multiply by 314. Well, one of these drops off, and so now I'm looking at 108 and 99. So I need 108 and 99 in the numerator and 314 in the denominator. So 27, my answer is A. All right. Number 28. In a recent survey, 60 randomly selected married couples from the same town were asked to rate overall quality of living in their town on a scale from 1, which is stinks, to 10, which is phenomenal, on 20 different attributes such as accessibility to major highways, availability, entertainment, services provided by tax dollars, etc. For each couple, the husband's individual ratings on the 20 attributes were averaged to produce an overall quality rating, and that process was repeated for the wife. Each point on the scatter plot below displays the overall average of one of the 60 couples, with the husband's rated represented by a horizontal axis and the wife's rating on the vertical axis. So basically, here it looks like the husband rated it at about a 4.5 and the wife rated it as a 2.2. So the husband liked it a little bit more than the wife. So whenever they give me a scatter plot, just a easy little tool that I kind of do that sometimes helps me out, sometimes it doesn't, is I go ahead and draw a line that's approximately 45 degrees, which in this case means that line right there. Now, I may not use it, I may not. It may be useful, may not be. But one thing I notice is, hey, you know what? These points are all below the line. And that's interesting because that means the husband is more favorable to this town on the whole than the wife. So let's see what we have. Husbands tended to rate quality of living higher than the wives did. Yes, and we know this because it's under the line. If it had been above the line, the wives' rating. So in other words, above the line, the wives strong carries it more. But below the line, the X value carries it more. So husbands definitely prefer this. So this looks pretty good. More overall ratings of 7 were assigned by husbands than wives. So I should be able to go here and go here. And it says more overall ratings of 7 or less. And it's like, no. These are the 7 or less for men. Almost all the women were 7 or less. So this is false. The wives generally rated at 7 or less. Whereas most of the men rated it more than a 7. The range in the husband's overall ratings is greater than the range in the wife's. Well, the range in the husband is about 4.5 to 9. So the range of the husband is about 9 minus 4.5. So about a 4.5 range, because that was high minus low. That's for the husbands. For the wife, our high value is also about a 9, but our low value is about a 2.5. So basically, they have a range of about a 6.5. So the wife has a larger range. The difference in overall ratings between husband and wife is not more than 3 for any couple. And I'm just going to bet real quickly that we can find somewhere on here where a husband has a high rating and the wife has a low rating. Here we have a husband of an 8 and a wife of about a 3 or a little over a 3. So that right there is a rating of a 5, a difference of 5. So that's false. You're like, well, how did you do that? It's like, well, that's about an 8 and that's about a 3.5. So 8 minus 3.5, 4.5, that's definitely more than 3. For each couple, the overall rating assigned by the husband was the same as the overall rating for the wife. If that were the case, it would be straight on the 45 line. It's not. So in this case, because it's underneath the 45 line, it's the X's are larger than the Y's. And in this case, the X's happen to be the husband's value. Husbands tended to rate it higher than the wives did. Wives don't like that place. Husband thinks is okay. Number 29. A 90% confidence interval is to be created to estimate the proportion of television viewers in a certain area who favor moving the broadcast of the late night weekend news to an hour earlier than it is currently. Initially, the confidence interval will be created using a simple random sample of 9,000 viewers. So we're initially starting off with 9,000, random sample of 9,000 in the area, assuming that the confidence, assuming that the sample proportion does not change. What would be the relationship between the width of the original confidence interval and the width of a second 90% confidence interval that is created based on a sample of only 1,000 viewers? So they're saying the proportion didn't change, confidence levels didn't change. All we're doing is changing the sample size. How do we do this? What happens to the width? Well, we're going to expect it to get wider. Why? Because as n goes up, the confidence interval gets narrower. They move opposite direction. So as n goes down, it gets wider. But there's a little formula that I kind of created that might help you with this. And it's always going to be 1 over, and I'm going to do the double fraction line. And then it's new over original equals 1 over. Well, our new was 1,000 and our original was 9,000. Now, real nicely, that simplifies to 1 over that. Now, I can use a little bit more about what I know because it'll make my life easier if I do. That's going to be 1 over square root of 1 over the square root of 9, which is 1 over 1/3. And 1 divided by 1/3 is 3. So basically, the second interval would be 3 times as wide. The second interval will be 3 times as wide. And all I did was essentially I did 1 divided by parenthesis 1 divided by 3 close parenthesis. 3 times as wide. If this had been so, because I had a smaller sample size, it's going to be wider. Smaller sample size, this one will be wider than this one. All right. Always have a smaller sample. When you have a smaller sample size, the interval gets wider. Okay, that formula works pretty well. Not a formula on the chart, it's one you'd have to memorize. All right, number 30. A new restaurant is interested in determining the best time temperature combination for roasting a 5-pound cut of lamb. The times to be tested are 45, 60, and 90 minutes at temperatures of 350 and 425 degrees, with the exception of the 90-minute 425 combination. All right, that combination is being eliminated because it'll overcook the lamb. So we're not going to do the 425 for this is not going to happen. All right. From 10 identical cuts of lamb, 2 are randomly selected to roast using each of the time temperature combinations in the sample oven. The quality of the finished lamb product is evaluated for each roast. What is the true? Which of the following is true? Well, I'm going to go ahead and, as much as I don't like doing these, I'm going to go ahead and make a tree diagram. And so I'm starting off with, I have a time, and I can sit there and go, well, I have 45 minutes, I have 60 minutes, and then I have 90 minutes. Well, that's one variable. But then it splits off. And I have a time temperature combination of 350 and 425, 350 and 425, 350 and 425. And you're like, oh, no, we don't have that one. We said we weren't going to do the 425 because that overcooks it. All right. Then we have 2 cuts of lamb, A and B. A and B, A and B, A and B, and A and B. And we count these up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that right there is our 10 cuts. So that's our 10 cuts of lamb. And it's like, hey, that makes sense because they said that we had 10 identical cuts. And at the very end, we're going to do this. We're going to evaluate the finished product. And I guess that's probably going to be, how does it taste? Probably check the thing out to see how it's going to be taste. So we have, in this case, this is an explanatory variable. This is an explanatory variable. So we have 2 explanatory variables. Our 2 explanatory variables happen to be time and temperature. So time and temp are the explanatory. So time and temp are explanatory variables. We happen to have our subjects, which are our 2 cuts of meat, and then we have our response variable, which is our finished product. So let's look at this. The explanatory variable is the quality of the finished lamb. No, that is the response variable. So this is wrong. The response variable is the roasting temperature. No, the roasting temperature is one of the explanatory variables. The experiment is repeated, identical results will be expected. They say that in science class because everything's controlled. But I don't know about you. Every time we do cook, it's slightly different. Usually because the meat is a little bit different, but there's other things that can impact it. But because the meat might be a little bit different, etc., we don't expect identical results. In fact, that's why we use multiple. We do it multiple times, is because it's like, you know what? We know the meat's going to vary. So overall, what's the average best? So no, it's not going to be that. There should be a control group in which no treatment is given. If I'm not giving it a treatment, that means I'm not cooking it for any time. I'm basically serving it raw. So I don't think that's appropriate. No control group would be no variable, no explanatory variables, no time, no temperature in this case. 2 cuts that were roasted are an example of replication. And yes, they are, because we want to find on average which one makes the best, because we know pieces of meat vary slightly. So on average, which one has the best outcome for the lamb? All right. So the answer to number 30 is letter E.